In this video, we're going to talk about increments and differentials, which is really starting to get into some applications of the derivative. So an increment, if we have a function y equals f of x, and we have two possible x values, x1 and x2, then the increments, delta x, or the change in x, and delta y, the change in y, are defined as delta x is x2 minus x1, the difference in the x values, so how much did x change? And delta y, also sometimes written delta f, is the change in the y values, f of x2 minus f of x1. So, for example, we have a function y equals f of x equals x cubed. If x changes from 2 to 2.1, so x1 is 2, x2 is 2.1, then y changes from, this is going to be y1, 2 cubed, which is 8, to y2, which is 2.1 cubed, which is 9.621. The change in x is called the increment in x, denoted by delta x. So delta x in this example is 0.1. And the change in y is called the increment in y, denoted by delta y, or sometimes delta f, which is 1.621. Delta x and delta y are numbers. Now, increments and the derivative. What's the relationship between what we've just talked about and the derivative? So we remember the difference quotient, f prime of x, is the limit as h goes to 0, f of x plus h minus f of x divided by h. If we let x1 equals x and x2 equals x plus h, then delta x is h, and delta y is f of x2 minus f of x1, which is f of x plus h minus f of x. Therefore, the derivative is the limit as delta x goes to 0 of delta y over delta x. Now, the thing that we're really going to use a lot, and sometimes we're going to use this without actually realizing, is the following. So we have increments and approximation. For small delta x, so again, remember that limit means that delta x is getting smaller and smaller. So for small delta x, you have the derivative, f prime of x, is approximately equal to delta y divided by delta x. Now multiply both sides by delta x and we find the following. Delta y is approximately equal to delta x times f prime of x. Now this yields the tangent line approximation. So delta y is f of x plus delta x minus f of x. It's approximately delta x times f prime of x. Or f of x plus delta x is approximately equal to f of x, this is just rearranging, plus f prime of x times delta x. So the value of the function a little bit away, delta x is some small number, from x is equal to the value of the function at x plus, is approximately equal to the value of the function at x plus the derivative times the change in x. So now we define differentials. If y equals f of x is a differentiable function, it has a derivative, then the differential dy or df in this case is defined as the product of f prime of x and dx, where dx is equal to delta x. So symbolically, dy equals f prime of x dx, or df equals f prime of x dx. So this f prime of x dx is, if we go back a page, this approximation here, right? So approximately, the value of the function when we make x a little bit different than the original, if we change x a little bit, is equal to the original function, f of x, plus the derivative times that change. So we've just called that the differential. So we want to find dy for f of x equals x squared plus 3x, and evaluate dy for x equals 2 and delta x equals dx equals 0.1. All right, well, dy is equal to f prime of x times dx. So we need the derivative. F prime of x is equal to 2x plus 3. Right? X squared, bring the exponent down, so we get a 2 times x to the 2 minus 1, which is 1, plus 3. Okay. We want to evaluate dy for x equals 2 and dx equals 0.1? Well, f prime of 2 is equal to 7. So dy is equal to 7 times 0.1, or 0.7. So there's dy. Now, delta x is equal to 0.1, because delta x equals dx. Delta y, this is the actual change in y, is f of 2.1 minus f of 2. So let's pull out a calculator. So our function is x squared plus 3x. So we want to do f of 2.1. So 2.1 squared plus 3 times 2.1, 10.71. So this is equal to 10.71 minus, let's see, f of 2 I can do in my head here. So that's 4 plus 6, 10. So 0.71. So you can see the actual change in y when x goes between 2 and 2.1 is 0.71. The approximation is 0.7. And the approximation, again, we can make that pretty good, but the approximation is close, right? 0.7 versus 0.71. And actually was a lot easier and quicker to calculate. So, one thing to remember. Very often you're going to find questions that ask you for approximations. They don't ask you to do calculations, they ask you to approximate things. If it's asking for approximations, then use differentials, not increments. If it's asking for actual changes, then use increments. So increments stand for actual changes in y resulting from the change in x. The differential stands for the approximate change in y, estimated using derivatives resulting from the change in x. Now, notation. We often write the derivative of a function as dy over dx, or df over dx, or ddx of f of x. So we often use differentials to write our derivative. So you're going to see this notation again and again, right? Instead of f prime of x, you're going to see dy dx or df dx. It all means the same thing. Okay, couple of problems. dy equals f of x. So we want to find dy for f of x equals 6x minus x squared. Okay, we want x equal to 2 and dx equal to 0.3. Okay, so remember dy equals f prime of x dx. Okay, so we need f prime of x. We take our derivative. Derivative of the first function is just 6 minus 2x. X is 2. F prime of 2 equals 6 minus 4 equals 2. Dx is 0.3, which means that dy is equal to 2 times 0.3 equals 0.6. Okay, so that suggests that, again, if we let's start at f of 2. So f of 2 equals 12 minus 4 equals 8, which means we expect f of 2.3 is approximately equal to 8 plus 0.6 equals 8.6. So that's our approximation. Let's calculate f of 2.3 just to see what it is. Again, I need my calculator. 6 times 2.3 minus x squared, 2.3 squared equals 8.51. 8.51. So delta y is f of 2.3 minus f of 2 equals 8.51 minus 8 equals 0.51. So dy is 0.6, delta y is 0.51. If f of 2 is 8, we approximate f of 2.3, this should be an approximate, as 8, oops, no, this one's exact, sorry. f of 2.3 is approximately 8.6 using differentials, and it's exactly 8.51, right? So that's an example using differentials. The next example, we've got dy. We want to find dy for f of x equal to the square root of x minus 3x squared, and compare dy and delta y for x equals 4 and delta x or dx equals plus or minus 0.1. So we've got two different dx values here. So we're going to find f prime of x. That's 1/2 x to the negative 1/2 minus 6x. We need to calculate f prime of 4 for both of these. F prime of 4 is equal to 1/2 times 1 over square root of 4 minus 24. So f prime of 4 is equal to, that's 1/4 minus 24, which is minus 23.75. Okay, so we'll calculate for dx equals delta x equals 0.1 first. Well, dy equals f prime of x times dx. So dy equals f prime of 4 times 0.1 equals negative 23.75 times 0.1 equals negative 2.375. Okay, so that's dx is plus 0.1. And dx equals delta x equals negative 0.1. Then dy equals f prime of 4 times negative 0.1, which is going to be 2.375. So those are our approximations, which means that f of 4.1 is approximately equal to f of 4 plus dy, which is equal to f of 4, that's 2 minus 3 times 16 is 48, that's negative 46, minus 2.375 equals negative 48.375. And f of 3.9 is approximately equal to f of 4 plus dy, which is negative 46 plus 2.375, which is, what is that, 43.625. If I've got negative 43.625. Now let's calculate f of 4.1 precisely. So f of 4.1, square root of x minus 3x squared. Let's grab a calculator. So 4.1 square root minus 3 times 4.1 squared equals negative 48.405. Negative 48.405. Looks like we did a pretty good approximation. And we want to do f of 3.9 as well. So 3.9, what was the function? Square root of x minus 4 times 3.9 squared, negative 58.86. Something went horribly wrong there. Let's try that again. Square root of 3.9. Let's just do it again. 3.9 square root minus 4 times, oh, it's not 4 times, it's 3 times. That's what went wrong. 3.9, oops, clear this out. Let's clear. There you go. 3.9 square root minus 3 times 3.9 squared equals negative 43.655. So f of 3.9 is negative 43.655. goes to show if you do the wrong function, you get the wrong answer. So again, we look at this, we calculated dy, did the differential. It gives us an approximate change in the y values to tell us what f of 4.1 is approximately, negative 48.375. We plug the numbers into our calculator, we get negative 48.405. Equally, f of 3.9, approximately negative 43.625. Exactly, plug it into our calculator, if we do it correctly, negative 43.655. So what we're doing is we are using derivatives to find ways to approximate functions, to see what the function is approximately equal to. We will use this idea, this concept, over and over again in this course in lots and lots of examples.